everyone, this is Mrs. Lopez, and today we are working on lesson 10 in our module 1. There is no new material that we are going to learn in lesson 10. We are just practicing doing operations with numbers written in scientific notation. I'll get you started on this. We will do together examples 1 and 2, and then you will pause the video and do exercises on your own. So here we go. Example 1. The world's population is about 7 billion. There are 4.6 times 10 to the 7th ants for every human on the planet. About how many ants are there in the world? So first, easiest way of doing some problem solving is to visualize the situation. We know that there is 4.6 times 10 to the 7th ants for every human, and there are 7 billion of those humans. So we probably want to multiply this number by this number to see how many ants there are in the world, right? So first thing that we want to do is to change the word 7 billion into scientific notation. 7 billion is 7 multiplied by 10 to the 9th power because billion has 9 zeros, right? So that is the world population. And we are going to multiply that by 4.6 times 10 to the 7th power. So this is basic multiplication problem. All numbers are multiplied by each other. There is no power raised to a power. This is just multiplication. So we are going to use the product rules for exponent, and in which we are going to multiply the 7 by 4.6, and we are going to add the powers of 10. So I'm going to just apply commutative property to switch numbers around, and I will write 7 times 4.6 and 10 to the 9th times 10 to the 7th. I did not change anything, I just rearranged the numbers. So now that I'm going to multiply 7 times 4.6, I will get 32.2. And that is going to be multiplied by 10. And I'm going to add the exponents. So 9 plus 7 is 16. And now that we have this, we can see that this is not scientific notation. We need to change 32.2 into scientific notation first, and we will put the decimal between 3 and 2. So we'll get 3.22 times 10 to the first power, and that is times 10 to the 16. So that becomes, and our final answer is 3.22 times 10 to the 17th. And that is how many there are ants in the world. So you can say, you can write the answer. There are 322 times 10 to the 17th ants in the world. Look how big of a number that is. Okay, example 2. A certain social media company processes about 990 billion likes per year. If the company has approximately 8.9 times 10 to the 8th users of the social media, about how many likes can each user responsible is each user responsible for the year? Write your answer in scientific and standard notation. So again, we are trying to visualize the whole thing, right? We have the total of 990 billion likes per year, and we have a total population of the people who use the social media. So this is the total population. So we have two totals, and we want to see how many likes per person per year. That seems like a division problem to me. So we are going to change 990 billion into, I'm going to write it in standard form first. 990, and then billion is going to be 9 zeros. I'm going to change this number into scientific notation. 9.9, and from here I see how many digits I need to move my decimal, and that is 11 digits. So times 10 to the 11th. And then we have our users of the social media, which is 8.9 times 10 to the 8th. We are going to divide one by the other. So here is our division sign. Since we are dividing numbers, we are dividing 9.9 by 8.9, and we will get about 1 and 1, 1, 2, 3, 5, and it will keep on going, times 10, and we are subtracting powers of 10 here since it's a division problem, 10 to the third. Let's round it to the nearest tenth. It'll be just easier for us. So it's approximately 1.1 times 10 to the third. So now this number is written in scientific notation. 1 is more than 1 and less than 10, and 10 to the third is the power of 10 here. And now let's change it into standard form because we do need to write that number in standard form. 1.1, and I'm moving my decimal 3 spaces to the right. 1, 2, 3. It's 1,100. And the answer to this problem is each user is responsible for about 1,100 likes per year. That looks like a real world situation to me. All right, so we did examples 1 and 2. Again, my tip for all the word problems is first to visualize the problem and see what you're going to do to find out the answer. Think about the process, create a picture in your mind, and then do the math. So pause this video, do exercises, and we will get back together in a bit. All right, so let's go ahead and review the answers. In exercise 1, the speed of light is 300 million meters per second. The sun is approximately 1.5 times 10 to the 11th meters from Earth. How many seconds does it take for the sunlight to reach the Earth? There is a formula to calculate the time when we know the distance and the speed or velocity, and that is when we divide distance by the velocity, we will get the time. And that's exactly what I did. First, I changed the speed into scientific notation, and I got 3 times 10 to the 8th, and then I divided that. So I took that and divided the distance, 1.5 times 10 to the 11th, by that speed. And so what I did, I divided 1.5 by 3, and I got 0.5, and I subtracted the powers of 10 according to the quotient rule of exponents, and that is 10 to the third power. Then I noticed that 0.5 times 10 to the third is not written in scientific notation, so I changed it into 5 times 10 to the negative first and negative first because I have to go back to the left 1 space to get to 0.5, and that is times 10 to the third. And finally, I combined the powers of 10, made it 5 times 10 to the second, or 500. That means that it takes 500 seconds for the sunlight to reach the Earth. So that was our number 1. Let's get to number 2. The mass of the moon is about 7.3 times 10 to the 22nd kilograms. It will take approximately 26 million moons to equal the mass of the sun. Determine the mass of the sun. Okay, so first I changed again 26 million moons into scientific notation, and I put my decimal between 2 and 6 and multiplied it by the power of 10 to the power of 7. And then since we are talking about how many moons it takes to get to the sun, and we know the mass of one moon, we know that we need to multiply. So I'm multiplying these two numbers together. I just rearranged these two numbers according to the the commutative property, sorry, and I've just multiplied these two numbers, resulting in 18 and 98 hundredths. And then I changed it into scientific notation, which is 1.898 times 10 to the first, and that is multiplied by the power of 10 to the power of 29, which is 1.898 times 10 to the 30th. So the mass of the sun is 1 in 898 thousandths times 10 to the 30th kilograms. Example 3. In 2010, Americans generated 2.5 times 10 to the 8 tons of garbage. There are about 2,000 landfills in the United States. Assuming that each landfill is the same size and that trash is divided equally among them, determine how many tons of garbage were sent to each landfill in 2010. So we know how much total garbage we have. We know how many landfills there are in total. We want to see the amount of garbage for each landfill, and that is a division problem. So since we want to find out how much garbage per landfill, we are dividing the amount of garbage by the amount of landfills. Again, we are dividing 2.5 by 2 is 1 and 25 hundredths, and we are subtracting powers of 10 according to the quotient rule of exponents. So we get 1.25 times 10 to the 5th tons of garbage were sent to each landfill in 2010. Think about how much garbage we make a year. Exercise 3. The mass of Earth is 5.9 times 10 to the 24th kilograms. The mass of Venus is this large of a number. So compared to Venus, how much greater is Earth's mass than Venus's mass? So one thing that you need to understand here, how much greater is not how many times greater. How much greater is basic comparison problem, which involves subtraction. If we had the word times in here, then we would divide. But there is no word times, so we are just subtracting. We are subtracting 5.9 times 10 to the 24th and 4.9 times 10 to the 24th. And that happened because we converted this large number into scientific notation. So since we are subtracting 5.9 and 4.9 and multiplying it by 10 to the 24th. So the Earth is 1 times 10 to the 24th kilograms heavier than Venus. Next problem is exercise 4. Using the information in exercise 3, find the combined mass of the Earth and Venus. From our previous problem, we know the masses of the Earth and Venus, and all we need to do is to combine them. So instead of subtracting how we did in exercise previous to this one, we are going to add them. 5.9 plus 4.9 is 10.8. We are multiplying it by 10 to the 24th. We are changing 10.8 into scientific notation, and that is 1.08 times 10 to the first, and that is multiplied by 10 to the 24th. And we are just adding the powers of 10, and that is 1.08 times 10 to the 25th. That is the combined mass of Earth and Venus. Exercise 5 and last exercise here is that the combined mass of the Moon, Earth, and Pluto is given here. How many combined Moon, Earth, and Pluto masses are needed to equal the mass of the Sun? The mass of the Sun is the whole big thing, right? So we want to see how many can fit into it, and that is a division problem. So we are dividing the mass of the Sun, which we know from exercise 2, by the combined mass of the three it's not planets or satellites, it's combined mass of Earth, Moon, and Pluto. So when we divide, we will get 0.3170, and we subtract powers of 10, which is multiplied by 10 to the 6th. So I just rounded here to the nearest hundredths, 0.32 times 10 to the 6th, and then I changed my 0.32 into scientific notation. 3.2 times 10 to the negative first because we are dealing with a small number, and that is multiplied by 10 to the sixth, combining exponents of 10, and we get 3.2 times 10 to the fifth. If I want to change that into standard form, I will get 320,000. That means that they will take 320,000 combined masses of Moon, Earth, and Pluto to equal the mass of the Sun. So that's how heavy the Sun is. Now, I would like to go over one more problem and just kind of quickly go over the addition and subtraction using different powers of 10. We did it in lesson 9, but I just want to give you a little bit of more practice here. So let's say the mass of the Earth is 5.9 times 10 to the 24th kilograms. The mass of Pluto is 13, and then we have this many zeros, kilograms. Okay, and I want to see the difference between the Earth's mass and Pluto's mass. So my question is, how much greater is the Earth's mass? So go ahead, pause this video one more time, one more last time, do this problem, and then get back to check the answer. Okay, so here we go. I rewrote this big number into scientific notation, and that is 1.3 times 10 to the 22nd kilograms. Because we are comparing the two masses, we are just subtracting one from the other. We are subtracting the mass of Pluto from the mass of Earth. 5.9 times 10 to the 24th minus 1.3 times 10 to the 22nd. Notice the magnitude of two numbers is different. We need to make sure that it has the same magnitude. So we're changing 10 to the 24th into 10 to the 2nd times 10 to the 22nd. And we're rewriting 5.9 times 10 to the 22nd in standard form. So we multiply 5.9 by 10 to the second, or by 100. We'll get 590 times 10 to the 22nd minus 1.3 times 10 to the 22nd. Then we are going to use distributive property to put 10 to the 22nd outside of the parenthesis and subtract the numbers inside. And we will get 588.7 times 10 to the 22nd. Now, 588.7 is not written in scientific notation, so we are going to rewrite that. 5 and 887 thousandths times 10 to the second and times 10 to the 22nd. We are combining powers of 10, and we get 5 and 887 thousandths times 10 to the 24th kilograms. That is the mass of the Earth. Is that how much heavier than the mass of the Pluto? Now, that is all for lesson 10. I hope it wasn't that complicated, and I will see you in class.